Okay, I will wait a little bit for you so that you can join there. Okay, thank you. Okay, so now let us start our lesson today. I couldn't see your faces last time. Were you so confused last time about that messy calculation or not? Yeah. So I don't know what was hard about that calculation. I don't want to repeat it again, but we want to continue our lesson, and so that we haven't spoken about integrals officially yet. Okay, what we learned is just we started with a motivating problem, and that was finding the area under the curve. And then we come up with this idea that it would be good if I can partition that area into rectangles and calculate the area of each rectangle individually and add them. And then if I increase the number of rectangles, then I will have a better and better approximation to the real area, yes? And then I hopefully, by demonstration on GeoGebra, I was able to convince you somehow that if you really increase the number of rectangles, then it would be a real good approximation to the area. And then we learned that if actually mathematically I send the number of rectangles to infinity, who cares? Yes, let us go to infinity. Yeah, if you want to go to infinity in real life, it's hard, but if you want to go to infinity in your imagination, it's super simple. I am just there, I'm in infinity now. Okay, you can imagine that. Okay, then we learned that, okay, this will probably give us the real area. Okay, and by the way, the logic is quite different. The logic is to take that as the definition of the area. If you really think about what area is, you need to have a definition what we call an area. So it might be, the logic is that I was trying to convince you that formula, the limit of the Riemann sum, let me write it here. So the limit of sigma f m sub k, you remember this m sub k was the midpoint of the kth interval multiplied by delta x, which is the width of all those rectangles, because I partitioned my interval to equal pieces. And then we say that k goes from 1 to n. So I am adding n of those rectangles, the area of n of those rectangles, and I will take the limit when n goes to infinity. Then this number, this part, is called a Riemann sum, yes? Riemann sum. And then we learned that the limit of a Riemann sum when the number of terms goes to infinity becomes a good way of defining the area under the curve of the function f of x with respect to the two lines, yes? Okay. But let me try. I want to give you the same kind of motivations that we had before. So do you remember when I wanted to talk about a limit, when I was teaching you derivative, I started with a limit like this. Limit of f of a plus h minus f of a divided by h when h goes to 0. Yes? So, and then I was trying to motivate you why this limit is important. People didn't know about the name of derivative. Okay? I told you that there were two scientists. One was Leibniz, the other was Newton. Leibniz was trying to solve a problem in mathematics, just mathematical curiosity. That problem was, if I have a curve y equals to f of x, and if I have a point on this curve, say that I know its x coordinate, my goal, actually his goal, was to calculate an equation, to determine an equation for the tangent line to the curve at that point. Yes? And then I tried to motivate you. If you remember, if you have forgotten, you can go and watch the video back, of course, if you care so much about these things. Then we realized that the k value of this tangent line, it becomes equal to this. I tried to motivate you, hopefully I succeeded, that this limit will give you the k value of this tangent line. Yes? Are you with me or not? Sleepy or not? Yeah, it's changed a little bit habit, yeah. But hopefully you didn't listen to me in bed. How many of you listened to my lectures when you were in your bed? Okay, hopefully not. Yes. Anyway, so this limit becomes this k value. And then I told you that Newton was thinking about a completely different setup. He was a physicist mainly. He wanted to actually find the instantaneous velocity of a moving particle. Okay, and then Newton also. So the formula. This was the k value for the tangent line, and he realized that if I want to calculate the speed, the instantaneous speed of my moving particle, which is moving along the x direction, say, it was also able to write a formula similar to this. T is time here, x is the location of the moving particle on the x-axis at different times, and he came up with this formula, if you remember. H goes to 0, and this gives Newton a way to be able to talk about the instantaneous velocity of the particle. So, but you see that they are very similar in structure, yes? So, but these problems actually rises in two different contexts. One is just a mathematical curiosity, playing with pen and paper, and then this is another problem Newton was solving in real life. A moving particle, we want to measure its, not measure of course is an experimental job, but he wanted to come up with a formula to be able to predict the speed, instantaneous speed of the particle, and then when we go and do the experiment, see that they match. Okay, and then you see that he came up with this formula. I hope that you immediately realize the structure of these two limits are very similar. Yes, only name has changed. The function which was denoted by f in Leibniz notation, it is now denoted by x, because we usually want to measure the distance from the origin, and it is better to call it x instead of f, but of course you can call it f. And instead of having, I don't know, a at a point, so you can have this is your time. So, but the structure are the same. So then I told you that by these two examples, and we can bring, of course, a lot of examples, that this kind of limit becomes important. And when it becomes important, mathematicians think in this way. So let us give it a name and try to explore and investigate the properties of this limit. And it gives rise to those beautiful structures that we have studied so far. I don't know. It depends what you call beauty, yes? But anyway, it was beautiful. And so I want to do more or less the same thing. We again started with a practical problem. We wanted to find the area below the curve, yes? I had a function. So let me just remind you what happened. I had a function, which is usually a curve, y equals to f of x. And then I want to restrict myself between two vertical lines, say A and B, and I want to find the area which is bounded by this curve on one side, but three straight lines on the other sides. I wanted to calculate the area here. And then we said that, okay, let us partition this interval to smaller rectangles, to smaller intervals. And then, for example, if I ask you what is the length of this interval, what is the length? What is the length of this interval? Here is A, here is B. What's the length?
B minus A.
B minus A. So here, from here to here is B minus A. From here to here is B. From here to here is A. So if I ask you what is the length of this interval, you would say B minus A. So I divide B minus A into n pieces, and then I want to send n to infinity. Each one of these numbers is called delta x, the increment in x, okay? For example, let us consider the kth interval, yes? The kth interval is somewhere between k, x sub k minus 1. I don't want to repeat a lot of things again. So we have this rectangle. So do you remember, I need to find the midpoint, and then I go up, and then construct this rectangle here. Yes, here. And this is one of those rectangles. So let me clean this. We don't need this. But this is, if I want to write something, this is the midpoint of the kth interval. Okay? And then I calculated the area of this rectangle. How? If I ask you what is the width is delta x. So I multiply delta x by the height. The height was from here to here. Do you remember? This is mk. So if I ask you what is the height, you put this number in your function, you get this number, f of m sub k. And then you multiply them. So this would be the area of this rectangle. Yes? And then you will start adding them up for all the intervals, from the first interval to the nth interval. But then you take the limit and send n to infinity. And this would be a reasonable value for what you call the area. Yes? So this was my problem here. But let us now assume this is extremely important to understand where this limit becomes important, okay? So this limit appears in this problem. Now let us switch gears and then try to think about another problem. Let me ask you one question. Assume that you have a particle. Again, I want to give you, this is just a mathematical curiosity. Let us take an example from physics as well, okay? So if I ask you, I have a moving particle whose speed is constant all the time. Assume that the speed of this particle is 2 meters per second. Always, okay? It's going constant, with constant velocity. Now I ask you, you wait 5 seconds. What would be the displacement of this particle in 5 seconds? What's the answer? I'm not sure that your brain is frozen. It was not my fault that day. So I have a particle moving with a speed 2 meters per second constantly, and then you wait 5 seconds. How much the particle moves in these 5 seconds? Everyone. What? 10 meters. Is that clear? Okay. But now the problem is that this is not very real situation, because it is very hard to keep the speed of the particle constant, exactly constant 2 meters per second. Now assume that you have a particle actually moves with different speeds. For example, let us consider the same time interval. I go from 0 to 10. Let us call it in this way. I go from the second T1A. I wait until T2, which is B. I start experiment when the time is A. I end the experiment when the time is B. Okay? If the particle has a constant speed 2, how much the particle would travel in this time interval? How much? First, you need to find how much I am waiting. How much I am waiting? You see, B minus A. Agree? How much I am waiting? I am waiting for B minus A seconds. Is that clear for everyone? And then I multiply this by 2. This will give me the displacement in this time interval. Yes? But now assume that the situation is not that simple. Assume that this particle is a crazy particle. It's actually moving with different speeds at different times. And you want to ask the same question. You are not changing this initial state. You are not changing this final time. The starting time of experiment and the final time of the experiment is the same, but the particle has changed to a different particle, which moves with different speeds at different instants of time. Is that clear what I'm doing? But now I'm asking you the same question. You immediately realize that this problem is not as easy as before. Yes? So let us understand this. This is extremely important to understand this. So you will say that, okay, in this problem it was simple, but now I have a particle which does not follow one speed. It is actually, its speed depends on time. At different moments of time, the speed of the particle is a different number. This means that the speed of the particle depends on time. Yes? It depends at which instant of time you are looking at the particle. So this means that the speed of the particle is a function of time. It's also a function of time here, but it's a constant function, yes? So you can say that v, the speed of the particle at any instant t, is equal to 2. You see, this is just a constant function. But here, assume that this is not a constant function, it's a function which depends on time. Now I want to ask you the same question. How do you think about the problem? I have a particle, its speed depends on time. At different instants of time, the speed are different. But still, I start the experiment at instant A, and I finish the experiment at instant time B, later time B. And I want to ask you, how much the particle has traveled during this time interval? I want you to think a little bit. I want you to try to understand the connection of this new problem. You will see that. Do you have any idea? Let us hear from you first. Yes, Dylan?
I thought maybe it would be b of t multiplied by b minus
a. Do you think that this is reasonable? Because what you are doing, you are taking the whole interval. Yes, the time interval is b minus a, and then you are multiplying by vt.
Yeah,
yes,
different.
It's different. That the speed of the particle is different at different instants of time. So the answer is not that simple. I hope that you understand that. Yes? Okay. But how do you think we can start thinking about the problem? So think about this so that I can clean this and try to draw another diagram for you. Let me just draw here. Let us try to do the same type of things here. Okay, let us draw a diagram so that the x-axis is no longer the x-axis, is the time axis. Okay, so let me call it time. Okay, and then instead of having this, let me call it the speed v. And try to draw the diagram of this speed. It's better to call it velocity. Velocity with respect to time. Yes? So for example, this is the point, this is time A, this is time B. For example, at time A, what is the speed? Assume that you have attached a speedometer to the particle and you can read the speed of the particle at different instants of time. So for example, here you see that the speed of the particle is 1 meters per second. I don't know, a little bit later, the particle is going 2 meters per second, and then suddenly it pushes the brake. I don't know, at some other instant of time you have this. But you want to consider all the cases. Then you will get a curve. So this curve will give you the velocity of the particle at different instants of time. Is that understandable? Is that understandable how I'm just thinking about something like that? So I will get a curve. This curve is in the xy plane, but this is also the curve, but it is in TV plane. Yes, the horizontal axis is t, the vertical axis is v. Now let us assume this. Let me chop up this interval into n pieces again. Okay, so what I'm doing, so let me just start actually breaking this, partitioning this interval to these intervals. For example, here, 1, 2, 3, 4, 5, 6 intervals. Okay, if I ask you how, so let me call this, let me call this one T node, T1, T2, T3, T4, T5, and of course this would be T6. Okay? So if I ask you how much particle moves here, probably still I want to use the Dylan's method, but this is I want you to understand. Let me write. I would write V at M1
the speed, I will take the speed at this moment of time, and then I multiply it by this length. Let me call this length to be delta t. Okay, do you agree that this is not the exact displacement of the particle? Do you agree? Because still, this is an approximation. What I am telling you, that let us take the speed of the particle. The speed of the particle is also changing from here to here. But if the interval is shorter, the particle doesn't have enough time to change drastically its speed, yes? The speed will change, of course, in this interval, but not as much as if you wait for so long. Do you understand what is the meaning? So the particle is again changing its speed, but because the time interval is short, the particle does not have enough time to change its speed drastically. Yes? So if I ask you, is this number the exact displacement of my particle on this interval? Definitely you will say no. But if I tell you, can you accept it as an approximation to the displacement on this interval, you would say yes. Is that understandable? Okay, let me do the same thing for here. I calculate this one. This would be m2. I will calculate vm2 and delta t. This will also give me a small displacement on this part. So now if I ask you how much in total the particle has been displaced approximately from this time to this time, what would be the answer? This is the approximate displacement of my particle during this interval. Yes? This is the approximate displacement of my particle during the second interval. Now let us consider from the initial time to the second time t2. If I ask you what would be the approximate displacement of my particle during from here to here, what is your answer? Everyone should understand that. Please, everyone. We have to add them together. Yes? Do you agree? So if I add them, it gives me a still. Do you believe that this is the exact value? No. But this is approximately that value. Yes? And then I will do the same thing for the next interval. Do you feel that this is happening the same? It's a v, it's a function at some point multiplied by this time delta t instead of delta x, and then I am adding them up. So still I am facing a Riemann sum. Do you understand that? Is that clear? Okay, now just I will answer you. One question. If I want to make this approximation a better approximation, what leverage you have? Everyone. Yes? An interval shorter. If I make this interval shorter, then this poor particle doesn't have enough time to change at all, okay? So I want to make it shorter and shorter and shorter. So it means that I want to send this delta t to the infinity. It means that I need to send these intervals, these subintervals to infinity, yes? If I send the subintervals to infinity, the number of subintervals, the length of each one of these time intervals will go to 0, okay? And then hopefully you agree that then the speed of the particle at this time is actually a very good representative of the speed of the particle on the whole interval, because the particle doesn't have enough time to change its speed. Yes, is that understandable? So now let us write. Can you write what my answer? If I want to ask you what is the displacement, how do you answer that? Write something for me. I want to motivate you that this way will give rise to a good way of measuring the displacement. What can I write if I want to write this? Do you see? I need to add them up. Yes. How many times? N times. Yes. So it becomes sigma v of m sub k delta t. I add them from the first interval, time interval, up to nth interval. And then I will take the limit when n goes to infinity. Yes? So what you get, if you see this one, do you agree that the structure of this limit is again the same structure that appears here? Is that understandable? So this is a good way to understand that this is the displacement of the particle from time A to time B. But look here, check this one with this one. You see, hopefully you agree with me, the structures are the same. You have a limit, sigma notation. Instead of having your function to be f, your function is named v. And because of natural reasons, your variable, instead of just famous variable in mathematics, here in physics, this is representing time. So we are denoting with t. But except for that, the structure is the same. But the problems are quite different. Here we didn't want to solve the same problem. Yes, here we wanted to find the area below the curve. Here we want to care about the displacement of a moving particle in physical reality. Is that clear? But both of them end up with the same format. So then again, mathematicians become excited. They would say that there is something deeper to this. Let us investigate, give it a name, and study it. Do you feel the analogy, yes? The analogy between these two problems which gave rise to derivative, and for example, these two problems which gave rise to the notion of integral that now I want to define for you. Is that clear? Now, so I just wanted to motivate you that this kind of sum appears, you cannot imagine in how many contexts. But this is important. Whenever you want to calculate something like this, you need to remind yourself of integrals. This is important because usually people can calculate integrals, and when I ask them, what are you calculating actually, they don't know. Okay? So the Newton's formula come into the game when you want to calculate this. Okay? But it doesn't help you to understand the connection of the problem that you are solving with the notion of integral. Okay? If you want to understand that, okay, this problem should be solved using integrals, you need to understand this connection. Whenever, in any context, you are facing to calculate such a limit, it means that your problem can be formulated in the language of integrals. Is that clear? Yes? Okay. So let me now define the integral formally. So let us consider this. Let f be a function that is continuous. This is the only one that you study in your lessons. So let f be a function that is continuous on the closed interval. Do you remember what was the name of closed interval? It includes its endpoints. So I have a function that is continuous on the closed interval from A to B, including the endpoints. Then this, okay, and then I would say that let delta x be equal to the length of this interval divided by n. And let m sub k be the midpoint of the kth interval. Okay, the following limit let me write it, limit of sigma k goes from 1 to n, f of m sub k delta x, n goes to infinity, is called the integral. So the better name is definite integral. So, but this is not used in your book, so I put it in pair of brackets. It's called the definite integral of the function f on the interval
on the interval and it is denoted by this symbol. You put something like this, and then you put a below, b above, and then you write your function here, and then you put dx. Okay, and now if I ask you, if I want to write it for short, so I would say that the integral from a to b, read it like this: integral of f from a to b is equal to this limit. This is the meaning of, this is the definition of the integral. So you see, again, I motivated you by starting finding areas that this limit becomes important if your goal is to calculate the area under the curve. For today, I gave you another example that this kind of limit becomes important in a completely different context, finding the displacement of a moving particle whose speed is not constant. Okay, and then by this motivation, I wanted to convince you that this limit is important. Again, it depends what you call important, but yeah, it is important. And then mathematicians realize that if something is important, let us give it a name to be able to call it and explore its properties. So now we call it the definite integral of the function f from a to b. Yes? So you see, integral can represent area. Integral can represent displacement. Integral can represent, I can probably give you an example, mass. Integral can represent everything that you are involved with this process. Whenever your problem can be solved using similar process, you need to remind yourself about the integral. But there is a big practical problem here. And that big practical problem is that I hope that last session I convinced you calculating this is quite hard, even for simple functions. Then Newton's jump in, and then he realized that we can calculate this sum. If your goal is to calculate this sum, you can calculate this sum in a completely different way. And that is the notion of primitive functions. Yes? I will start yawning now. Are you sleepy or not? Hello? No, I could feel that. Why couldn't you answer me last time? Are you sleepy or not? Do you want to relax a little bit, come back again? Wash your faces or something? You are not the normal guys in here. Okay. Anyway, if you think that we need to have a rest, let us have a rest. Do you want to have a rest or not? Everyone is okay? Yes? Okay. Okay, so this is the limit. This is the definition of the integral. By the way, integral, this symbol of integral, it is similar to what, do you think? Yes? What do you think that this symbol is similar to? You can start from here. Let's stretch it a little bit, and then stretch it actually. So actually that's correct. So this integral sign is this stretched S. Do you think that this is a reasonable name or a reasonable notation? So is that a reasonable notation? So is it reasonable to call the difference sum? It's not reasonable, but here it is reasonable because what you are doing when you are calculating this integral, what you are doing, you are summing things up, you're adding things up. So you are calculating a sum, but the crucial difference is that what is the difference between this sum
without limit, and this sum. This sum is a discrete sum. You see the values jump from 1 to 2, and then from 2 to 3, and from 3 to 4. Okay? In sigma, you are adding things up, but your sum is a discrete sum. Your counter cannot take on any values between 1 and 2. It is 1. In the next step, it suddenly becomes 2. In the next step, it suddenly becomes 3. Yes? But when you multiply it by delta x, when you send n to infinity, it means still I have discrete sum, but the intervals are getting shorter and shorter. So it means that I am finding a very smooth sum when I am sending n to infinity somehow. That smooth sum is actually this integral. Yes? This is the meaning. So when you are facing an integral, you are summing things up. But that is a very extremely tool by limit. Let us explore that. What happens for delta x? Can you tell me? So what happens? Do you remember delta x was this? If I start increasing the values of n, what happens to this delta x? When I put n equal to 1, it gives me b minus a. I make it 2, b minus a divided by 2. I make it 3, b minus a divided by 3. So what is happening for delta x when I start increasing n? It gets smaller and smaller. Do you think that this will ever be equal to 0? No, because a fraction, if the fraction wants to become 0, its numerator should become 0. But b and a are different. So b minus a is never 0. But by increasing the value of n, I am making delta x shorter and shorter. Okay? So it is very strange. You see, if I ask you what is the limit of delta x limit when n goes to infinity, can you answer me? Only the limit of this part. It's clear. Divide it infinitely many times. Intuitively, what is left? What is left? Nothing. Yes? So it becomes 0. But isn't it strange? In the limit, it becomes 0. So if you multiply 0 by everything, it becomes 0. It doesn't matter how many times you add zeros. You should get 0. But if you do this process, you get a finite number, a finite value. This is a very surprising thing. So it means that this is the calculus of infinitesimals. It means that if I have infinitely many infinitesimals, I will end up with a number. But if I have infinitely many zeros, I will end up with exactly 0. And that is not useful. That this is very simple for exam, yes, because every answer would be 0 at the end. But yeah, unfortunately from your side, it is not the case. It depends to the behavior of the function. So that is extremely powerful, even though you are making this very small and very small, but it is not 0. You can call it negligible. The term, mathematical term, is infinitesimal. So if you have infinitesimal numbers, adding them together, you will get a finite value. And that value is something that you can be happy for it, okay? Okay, so this is another thing. And let me discuss about this delta x here. Delta x is the infinitesimal version, dx is the infinitesimal version of delta x. When I would say that this, in principle, dx is the infinitesimal version. It is a very short length compared to delta x when n goes very high. This doesn't have any particular role in your lesson. It is called the differential of x, but be careful. Don't be lazy not to write it. If you don't write it in the exam, you will lose some points. You need to respect the way that I write an integral. Integral from a to b, f of x dx. Okay, but if I ask you what is d of x, you can imagine d of x is the delta x, but the short, very, very short version of delta x. Okay, now the problem is that, let me now tell you the Newton's formula. So the Newton realized that calculating these sums are very messy, but it is super important in different contexts of science and engineering, mathematics and everything, okay? So he wanted to find a way to find this sum very easily, and he succeeded to do that. He found this formula. He realized that if you want to calculate this integral, you really don't, even though this integral is that sum, but you don't need to calculate it using the sum. You can use this technique. You can calculate a primitive function for your function, and then put the upper bound here, upper limit here, and then put the lower limit here, and then simply subtract them. So that is the very interesting formula of Newton. So again, you be careful. Again, you are calculating the same thing, but in a different way. You found, instead of calculating it through that very messy calculation, which sometimes becomes impossible, Newton actually posed this method. He said that I was able to prove it, that instead of doing that method, you can just think about finding a primitive function for your function. When you found it, put the upper bound, this is called, by the way, upper limit, lower limit of the integral. Put the upper limit into that function, it becomes a number. Do the same thing with the lower number, and then subtract it. What you get is your answer. You really don't need to go through that tedious process. Okay? So for example, if I ask you to calculate integral from 0 to 1 x dx. So what is the answer? What is the function here? The function is x. I need to ask myself, do I know a primitive function for x? This is your previous lesson. What is a primitive function for x? What is a primitive function? X squared divided by 2. So what you say that you put x squared, and by the way, there is another symbol to use. It's better to know that this is also used in the book. They write capital F of x, and they put a vertical line, not the integral sign. A vertical line in front, and write it like this. If you see something like this in the book or any other books, this means this. Okay? Okay, and then what you do, you write x squared divided by 2. You don't need to consider the constant c. I will ask you why. A primitive function is enough. You don't need to find all primitive functions. And then you write a line, and you write from 0 to 1. Okay, and then what you do, you put 1 instead of x and calculate it. You put 0 instead of x and calculate it. And then you subtract them, the number above minus the number below, and the answer would be 1 over 2. And then you can have an easy life. So you really don't need to calculate that mess. So is that understandable? And I have to teach these things because they are included in the book, and I always care about your understanding, not just memorizing things and doing things. But the good news is that for the exam, you need to be able to do this. So that's it. Okay? So most of the time, you want to calculate an integral. You need to ask yourself, can I find a function whose primitive function is this? So that primitive function lesson is very, very important. If you don't understand that, you will not be able to solve the problems in the exam. But as soon as you can give me a primitive function, Newton's told me how to calculate it easily. Now one question, why do you think a primitive function is enough? Yes? Exactly. So it doesn't matter which primitive function I choose. Assume that you choose a primitive function with a constant c. The constant c appears here and there. And when you subtract them, that constant is gone. So this is why a primitive function for this purpose is enough. Never ever write that c to bother yourself when you are dealing with definite integrals or in this type of integrals. Okay, now let me ask you another question. How can you interpret, this is important, how can you interpret this integral as an area? Can you tell me this number represents which area? Can you draw a graph for me to say that, okay, this integral represents this area? Yes?
The area under the curve between
1 and? No, 0 and 1 is correct, but which function? X. So it means that if I ask you in the exam, draw a graph so that that area is represented by this integral, you would say that, okay, I draw the graph y equals to x. Hopefully you know that this is this bisector. And then I start from 0 to 1, and then I go vertically. This would be this area. Okay, and now let us calculate, by the way. You know this is a right angle triangle. What is the area of this right angle triangle, by the way? From here to here is 1. From here to here is also 1. So what's the area? 1 times 1 divided by 2 is 100. Yes? Is that understandable? Okay, so for example, let us consider this case. Integral from minus 3 to 2 x to the power of 2 dx. I want you to calculate this. Okay, so how should I do that? Yeah, please come with me because I will give you more examples. How should I do that? You see, first of all, this is an integral. Everything is clear. Let me call something. What is your function? By the way, this is a word in English books. This is called integrand. Integrand means the function under the integral sign. That is called integrand. I think it's also in Swedish like that. So integrand is actually this function. This is called the lower limit. This is called the upper limit. Remember these names. If someone asks you what is the name of dx, you would say it's called differential of x. But the differential of x, if someone asks you what that is, you would say this is the very infinitesimal version of that delta x in Riemann sum. That's it. You don't need. But you have to write it all the time. I will give you what is another rule for dx for you. Okay, we want to calculate this. How should I do that? We always use the Newton's formula. So it means that I think about a primitive function. Okay, tell me, what is a primitive function for x squared? Everyone. Yes?
x3 divided by 3.
x3 divided by 3. Okay, be careful. You have to respect the punctuation rules. When you do a primitive function, you have to cross this over. I have seen people write it again here. No, that's wrong. You have to put this vertical line in front and write -3 here and 2 there. When you found your primitive function, you're no longer allowed to keep this. You have to write it in this way. And then what I have to do, this is my experience, and I advise you to do this method. Of course, this is not mandatory. You can do it in one line. But I have seen many students mess up the negative sign sometimes. I prefer, at least for the beginning, to chop it into 2 parts. What I have to do, I have to replace x with the upper bound, upper limit to the 3 divided by 3. And I patiently calculate it exactly, not approximately. 2 to the 3 is 8, 8 over 3, that's it. Then I go here and I replace x with -3. So it becomes -3 to the 3 divided by 3. I patiently calculate that. It is -27 divided by 3, but of course that is a better name, -1. When my calculations are done, I go back to horizontal line. I write the number above minus, this minus is coming from Newton's formula. Okay? But minus the number below. Accidentally, the number below has an extra negative sign. So be careful. And then I calculate it. It becomes 8 over 3 plus 9. If I calculate that, 35 over 3. So it is 35 over 3. That's it. This integral is this number. But if you want to interpret this number as an area, you might interpret this number as a displacement. You might interpret this number as a mass, electric charge, potential, everything that you can imagine. Integrals are ubiquitous in mathematics. So if you don't want to calculate something physically, or if this is not associated with any quantity, that's a pure number. But if this is going to be area, you have to write the area units here. If this is electric charge, you have to write the units. But can you interpret it now for me as an area? How should I interpret this as an area? If I want you to sketch a rough graph to show me a more
pictorially, so that what is the meaning of this integral with respect to the area? Yes?
Draw the function x2.
X2, so let me just do it step by step. The function is x2. You know something like that. This would be this. I just want to sketch. I don't want to be precise, okay? And then
And then -3.
-3, for example, assume that -3 is here, up to 2. It's a little bit, for example, shorter, and then it means that I go vertically up. So what you calculate is this area. Okay, so if I ask you to calculate this area, so you need to understand both of them are in the book. Sometimes you ask to calculate just the integral. Sometimes the graph is given to you, and they ask you to find the area of the colored region. So you need to be able to do it yourself. You need to be able, by looking at the area on the picture, you need to be able to write it in the form of an integral and solve that integral. Is that understandable? Yes or no? Okay. Okay, so let us do some examples. I want to write some of them here for you. So let us just write some examples. Integral from 1 to 2, 3x squared plus 5x minus 1 dx. We want to calculate this. So the number of examples would be very limited. I will not give you a lot of these examples because the hard part is not the new lesson. The hard part is finding the primitive function. Because if you know how to find the primitive function, I would assume that this is a simple calculation for you at this level. So this is why I will not give you a lot of examples of calculating definite integrals. They are easy, yes? But I will give you these kinds of problems that you need to interpret the area in the language of an integral and then calculate the integral. Okay, so that is something that you need to learn. Okay, I think you should be able to solve it. Now help me to solve it. How should I solve it? I need to ask to find a primitive function. You see, this is completely the old lesson. This is extremely important to know how to find a primitive function.
What is a primitive function of this? Can you do it in your head? What's the primitive function of this expression? What is that? Yes, what is the primitive function for this? Yes, please.
X to the power of 3 plus 5 over 2 times
X to the power of 3, very good, because you actually cancel the 3 coming out with that 3, very good. 5 over 2x squared, thank you. And then the last one?
minus x.
Minus x. Okay. Am I allowed to write the integral sign again here? No. What should I write? I have to write is this vertical line from 1 to 2. That's it. And then what I need to do, that's up to you, but I recommend you at least the first few times do it in this way. So you put 2 there everywhere. Instead of x, you put 2. It becomes 2 to the 3 plus 5 over 2 times 2 to the 2 minus 2. And patiently calculate everything. So it is 8, and then this is 4, this is 10. Minus 2, it's 16. Yes? So that's 16. And then I put 1 here, so it becomes 1 to the 3 plus 5 over 2 times 1 to the 2 minus 1. So this becomes 1 plus 5 over 2 minus 1. So this is clearly 5 over 2. When this is settled down, you go back to horizontal line. You write what you got above, and you put a minus sign because of Newton's formula, and write what you got below. And then what you get is 27 over 2. Yes? So do I need to put a unit there? In this problem, no. That's a pure number. But if this is going to be interpreted for the area, for the volume, I don't know, for what arc length, all of them involves integrals. Okay? So if you want to do that, then you have to write the unit. But here, that's the end of the problem. Let me just give you one more example, because I want you to realize the way that you have to write. If I give you this integral, please calculate this one for me as well. So from 4 to 9, x square root of x dx. I want to wait a little bit for this one, because I told you that there is no point to give you a lot of examples. I have already given you a lot of examples for finding primitive functions. What you need to do is to subtract 2 numbers. So we want to calculate this integral from 4 to 9. By the way, sooner or later you should be prepared for the next exam, yes? Because this lesson is actually finalized. But I want to solve 1 or 2 sessions for problem solving to improve your skills, then give you some time to practice, because we need to immediately go to the next chapter. And the next chapter is completely different. It's trigonometry and geometry. Okay, can you help me now to answer this? The reason that I gave you this example is not because I don't believe you can solve it. It's simple. I want you to teach the punctuation rules. The way that you have to write it properly if you want to write it in the exam. Okay, so can you tell me what is the first thing that I have to write in front? The first thing that comes to your mind, you need to find a primitive function for this. So do you remember your lesson from primitive function? Am I able to directly give you the primitive function in this form? No. What was the rule? Do you remember? What should I do here? Yes, Dylan?
You simplify.
How?
You like convert. Like if you take the square root of x, the exponent is 0.5.
Exactly. One. Okay. So this means that I have to repeat the integral sign. Be careful. This is the reason that I brought this example. So here, I have to repeat the integral sign because I haven't reached to that stage that I want to find a primitive function yet. My goal here is to simplify this expression, and you already know how to simplify. Let us not waste the time here. This is x times x to the power of 1/2. X times x to the power of 1/2 is x to the power of 3/2 and dx. So you see, don't get confused. I told you that you're not allowed to put the integral sign here because you were able to find the primitive function immediately. But here, I am repeating again, you have to write the integral sign because I haven't calculated a primitive function yet. Now, I want to find a primitive function. What is a primitive function for this? It is x to the power, if you have forgotten, let me write it patiently. This divided by 3/2 plus 1. Am I allowed to keep the integral sign here? The answer is no, because I did the primitive function part. And then I put 4 and 9 in front. So you see, this step is necessary. If you omit this integral sign here, that is wrong. You have to keep it, and you have to omit it here. You have to drop it here. Otherwise, it is wrong. So I want you to learn these punctuation rules, okay? So here, what I want to do, I want to simplify this. 3/2 plus 1 is 5/2. So this becomes x to the power of 5/2. This is the same number, but it is in the denominator. So it becomes 2/5. Do you remember we practiced for this quite good exercises? And then I go from 4 to 9. And then, according to Newton's law, according to Newton's theorem, I would put 2/5, 9 to the power of 5/2, and then I would do the same thing here. 2/5 times 4 to the power of 5/2. Okay, can you tell me how should I calculate this? What is 9 to the power of 5/2?
You can make it 3 to the power of 2.
3 to the power of 5.
Yeah.
Ah, yes, in total I said. Yes, you are right. You say 9 is 3 to the power of 2, and then you have to the power of 5/2. You multiply the powers, the exponents, it becomes 3 to the power of 5. And this is how much? 243, yes? 243 multiplied here, it's 486 divided by 5. That's the number. And then you go here. You do the same trick. 4 to the power of 5/2 is how much? Is 2 to the power of 2 to the power of 5/2, the same reason. So this becomes 2 to the power of 5, 32. So this becomes 64/5. Yes? And then you have to subtract them. So how? Don't get confused. Be patient a little bit. I have seen students miss points because of negative signs and things like that, which is, of course, annoying. So be careful about that. And that is easy calculation. Yes, it becomes 2, and 4/5. So this is your number. But my point is not this number. My point is to respect this part. If the primitive function is not evident in the beginning, and if you are simplifying this, you have to keep the integral sign until you are ready to write the primitive function. And at that point, you have to drop the integral sign and write this vertical line in front. Is that understandable? Yes? Okay. So do you have the book with you? Can I borrow it? So let us see if there's a good exercise in the book that we can also do that. So mainly I would say that we finalized the lesson part of this chapter. Okay, so there are some good problems here. Okay, no, we need to do something more to be able to finalize this chapter. Yes. Yeah, there are very good exercises, by the way. So I want you to think about them yourself first. So let me give you
a little bit time to practice. So if you want, you can start reading page 169 and 170. And there are exercises on page 171 and 72. They are very good exercises, I would say. So try to solve them. And next time on Friday, I will complete everything which is left. Okay, there is one, yes, there is one thing I thought that this is just in Math 4. No, you also have it. So you see, the next problem would be, thank you. The next problem would be what happens, because even we started from this part, you might ask yourself, okay, what happens if I have an area like this? Both of them are curves. Okay, so that's also possible, yes? So far, we learned this. We learned that we have a curve, but we have 3 straight lines. This region is limited between a curve and 3 straight lines. Let us relax them one by one. Okay, now let us consider 2 straight lines, but 2 curves. This would be the next lesson, and then we will go, okay, for this chapter. But you need to practice a lot because I should immediately start the next chapter. Yes? And that chapter is also very important because the next thing that we start in Math 4 is we start from trigonometry, that we end actually this chapter. So be careful that you learn it very good. No questions? Okay. Thank you for being here. So I end this live stream. I go to Zoom if you want to ask me questions. Thank you.